Let's talk about quadratic applications. There are two main types of quadratic application problems we're going to be seeing. The first type is when they talk about an increase in area. So a lot of times on these problems they give you a rectangle or a square and then they talk about how that area has been increased. So when they have these problems, you want to draw the rectangle or draw the square. And what we know about rectangles and squares are that their opposite sides are equal, the rectangle. So if they give me this side as x, and we would know that side is also x. And maybe they tell me that the length is 1 less than twice the width. They could be fancy. So we could say 1 less than twice the width might look like that. And when it's a rectangle, we know opposite sides are equal, so we have all four sides, even if they only tell us that the length is 1 less than twice the width. That's enough information. But then maybe they say that the length and the width of that rectangle were increased by the same amount. Maybe this is a swimming pool. Maybe they've added a sidewalk around the swimming pool. So we could draw the swimming pool sidewalk, and let's say we're adding 3 feet of sidewalk to each side of the pool, and we're adding it all the way around the edges. So the new size of that side of like my swimming pool and the sidewalk would take up 3 on both sides. So this new side here would actually become x plus 6 because you've added 3 feet on either side of that swimming pool. The same thing here for the length of the pool. You've added 3 and another 3 here. So the new length of the swimming pool, let me move my square out of the way, would actually be 2x minus 1 plus 6, which would become 2x plus 5. Now they ask you to find the new area of that swimming pool, for instance. So we might have to take the length of the swimming pool and multiply by the width of the swimming pool and go from there. So this would be a sample of what they could ask you about. We're going to look in a specific example in just a minute. And the same thing for a square, but keep in mind a square is different than a rectangle, so you even know more about a square if they tell you, they could tell you nothing about the square. If you know nothing, you still know that all sides are equal. If they tell you all sides are 3x, you could label them that way. But keep in mind that a square has all sides equal, so that's a lot of information, and that a rectangle has opposite sides that are equal, which is also good information. Now the other type of problem you're going to see often with quadratics is the path of an object. Usually this is a ball, a rocket, maybe they drop something from a tree, all kinds of stuff like that. So, for example, most often you're going to need the first quadrant of your graph for the reason being that time is only measured in positive units. We don't go back in time, even though there was Back to the Future. It really doesn't happen. So we have time is going to be positive, and over here you're going to either have height or you might have distance traveled, but time is always our x value because everything depends on time. Time is our independent variable. So let's say we have a path of a ball that's been hit by a baseball player. Maybe it was a basketball and it was thrown by a basketball player. Well, then it would not make sense for our graph to start at 0 because the baseball player is standing up and he's hitting a ball that's not flat on the ground. So maybe the baseball started at the height of 3 feet. But maybe the basketball player, who's nice and tall, like myself, had thrown the ball from his hands, and maybe he's 6 feet tall, and he's even reaching higher than that when he's shooting the basketball. So maybe it's 8 feet at that point in the air before it released from his hands. So you want to keep those things in mind with these problems, is what's the starting point? Did it start on the ground like a soccer ball? Did it start a little bit higher than that, maybe like a baseball or a tennis ball? Or was it even higher than that, like a basketball? The rocket problems usually start on the ground because, as you've seen on TV, when rockets launch, they actually start from ground zero. So they'll go up in the air, whatever the case may be, basketball, rocket, baseball, and they'll hit a maximum point. Of course, some of those vary depending on the sport, or if it's a rocket, it's certainly going to go higher than a basketball. So you'd have a maximum point right here where after a certain amount of time, you're going to have a certain height. Maybe you'd have a certain distance. So it could be either one, depending on what they're talking about. And then it's going to continue to fall back down to the ground. At some point, it's going to come all the way back to the ground and hit the ground. And a lot of times they like to ask you about this point, and it's really a zero of your graph. So you have your y-intercept where the graph will start. You're going to have a maximum vertex for these problems because these are all positive and they're going up in the air, so it's always going to be a maximum vertex. And when it hits the ground, you're going to consider that to be a zero. They could also ask you for any point on that curve, which once you have your function is going to be pretty decent for you to find in your table of your calculator, or you could plug in an x value to figure out the y value, so you can figure those out after you get a nice sketch and you have your table. So let's look at two specific examples of these. Just two, but I want you to write them down so you'll have these nice two examples in your notes. So for the first one, the sides of a square are all increased by 3 centimeters. The area of the square is 64 square centimeters. They want us to find the length of a side of the original square. So since they did not draw a square, that would be the first thing you want to do. So we draw a square. They did not tell me the sides of the original square, so that's my variable. So all I know is that they're all the same. So we could go ahead and say they would all equal x. If we don't know anything else, we do know that they're equal. They're all increased. So if you like to underline some important stuff, that would certainly be an important piece of information. They're all increased by 3 centimeters. So now I have a larger square. So my new square is x plus 3 and x plus 3 on all sides. But if I'm dealing with area, I really just need 2 sides because I'm going to multiply them together. So we have the area of the square is 64 square centimeters. So now we can set up our work. We've got our picture and we labeled it properly. So area is length times width, which are going to be the same since it's a square. So we have x plus 3 times x plus 3, and they've given us the area is 64. So we can set that equal. And then we can go ahead and start solving. So to solve this problem, you want to use the FOIL method since you see you have a binomial times another binomial. So let's start there. And we can use the box method or the FOIL method or the distributive method here. But we'll end up with x squared plus 3x plus 3x plus 9. So we end up bringing down 64 for now. Equals x squared plus 6x plus 9, because those terms in the middle combine to be 6x. Now, when we have a quadratic equation, that means we have an x term that's squared and we have a term that's not squared. The only way to separate those two and solve for x is to use one of our quadratic methods. And one of the most popular quadratic methods is to solve by factoring. So whenever you can, you want to try to solve it that way because it would take the least amount of work and give you a very nice answer that's easy to understand how it relates to your graph and how it relates to your problem. So let's try that. Let's subtract 64. So the first thing we have to do is get everything on one side equal to 0. So I bring down x squared plus 6x. 9 minus 64 is going to be negative, let's say 50. Let me see. 64 minus 9, we take away the 4, 55. Let me double check my work. Yep, okay. So 55, excuse me, 55. Just to make sure I got the right numbers. So we have a trinomial with a equal to 1. So that means we're going to need to multiply to come up with negative 55 and add up to get 6. So numbers that will multiply to be negative 55 and add up to be 6 would be 11 and negative 5. So we could put in our numbers. We have x plus 11 and x minus 5. So now to finish solving, we set each one of those equal to 0 and solve. So we get minus 11, x will equal negative 11. If we add 5, let me write that a little bigger. We get x equals 5. So we have two answers. X could be negative 11 or 5. But see, one of those does not make logical sense with our problem. If we're talking about a square and how much that square was increased by, negative 11 would make no sense. So we can actually mark that one out in this case and just stick with the 5. So our original square was 5 centimeters for each side. So then we have our answer. Now let's check out a problem that involves the path of an object. So we can see one of those. And again, I do want you to write this down so you have a nice example to have in your notes for when we practice these. So suppose you throw a baseball into the air with an initial upward velocity of 29 feet per second and an initial height of 6 feet. How many seconds pass before the ball lands? Okay, so without even solving this problem, we can go ahead and we can draw a little picture over here. If we know the initial height of 6 feet is where my ball started from, we can put that right here. That's going to be at time 0. It is 6 feet in the air. We know this ball is going to go up and it's going to come back down and land somewhere. So we can sketch. It started at 6. It's going to end over here. And if I want to know how many seconds, remember time is down here at the bottom. Usually it's in seconds, but it could be other units, but a lot of times they use seconds. How many seconds pass before the ball lands? So that is the number I'm looking for right there, which if you notice is a 0 of my graph. So to find a 0, we usually can solve by either factoring or we can find it with our calculator, or you can use some other methods that we'll talk about later. But factoring is what we're going to use again here. So they gave us our function. See, height is a function of time, negative 16 t squared plus 29t plus 6. The negative 16 is a popular piece of these functions because it has something to do with the gravity, the pull of gravity on this object. So let's start over here and write down our function. So negative 16t squared plus 29t plus 6. And if we take out the negative, we will have 16t squared minus 29t minus 6. Because you don't want to factor with that negative right there. And then we can start working on our trinomial. So we have 16 times negative 6 will give us negative 96. We want to add up to be negative 29. So I'm going to cheat and look at my answer over here that I already worked out. So negative 32 times 3. That way y'all don't have to wait for me to calculate. Okay, so we have negative 32 times 3. Leave our negative and we factor using 16t. Remember, put it in both parentheses for now. Put in negative 32 and positive 3. And then we need to take out 16 or factors of 16 because we have one too many. So if I take out 16 right here, I would have t minus 2, 16t plus 3. So now we need to take each one of those and set them equal to 0. So if t minus 2 equals 0 and 16t plus 3 equals 0, we could add 2. So t might equal 2 seconds. Or we subtract 3 and divide by 16. Now notice right there, t would be negative 3 over 16. And time is just not going to be negative. Not yet anyways. So we can't include that one. That one makes no sense. So 2 is our magic time when the ball will hit the ground. So 2 seconds we have figured out. So if you remember from our previous lessons, the negative is just that this graph is going downwards. It's facing down, and it has a maximum value. Now this problem did not ask us anything about the maximum height of the ball or when did it reach its maximum height, but we could figure that out. But for this example, we're going to just stick to what they asked us for. So it took 2 seconds for the ball to hit the ground. It started at 6. At a time 0, it was 6 feet. It did reach a maximum height at some point, and it came down and hit the ground after 2 seconds.